Hello everyone, I am Alex, CEO and leader of the architect team from Lexart. Today we are going to explore the architecture and mathematics behind our predictive middleware for asynchronous token estimation, specifically tailored for ultra high speed models like Gemini 3 Flash. Let's define the problem to solve. For high speed inference, model process massive context so quickly that unmonitored generation can cause budget exhaustion. Because these models are stochastic and autoregressive, we don't know if an output will be 10 token or 4,000 until it's finished. We need a way to predict this consumption and protect user quota. But any safeguard we put in front of API must operate in single digit milliseconds to avoid create systematically a bottleneck. To achieve prediction without latency, we had to introduce a core paradigm shift. Instead of passing the massive dense context of a prompt through heavy neural layers to guess its length, our system extracts instructional features. We look for semantic cues of verbosity and pass those through ultra lightweight proxy models. This shift from full context evaluation to intent parsing is what keeps our latency strictly marginal. Here's how that look our middleware gateway pipeline. Every client request hits the entry point and it's immediately intercepted. A local sentence piece tokenizer precisely counts the input token offline. The text then moves to the feature extractor, which hand it out or MoPE router. Finally, the system hits the budget guardrail, a decision matrix that either approves the request and passes it to Gemini or totally blocks if the predict cost exceeds the user quota. Let's zoom in on that routing phase. This is our mixture of prediction expert. The feature extractor uses a TF-EDF vectorized to efficiently map the prompt. Then a lightweight classifier categorizes the intent and hands the prediction task to a specializer regressor. We call this expert by routing a coding prompt to a code generation expert and the summarization prompt to a long form expert. We achieve highly specialized, accurate prediction at incredibly high speed. But the speed isn't our only challenge, safety is. If we train our proxy model using standard mean regression or mean squared error, the model learns to predict the absolute static average. Mathematically, this means it will underestimate the actual token output. In production environment with hard financial limit, a 50% underestimation rate is catastrophic failure. We need a stricter mathematical approach. Our solution is Quantile regression. Instead of predicting the average, we ask our model to predict the conditional quantile by setting our safety threshold to the 85th percentile. We mathematically guarantee that the actual output length will be strictly less than our prediction, the vast majority of the time. To train the MoPE router to do this, we use the pinball loss function. This asymmetric formula heavily penalizes the model for underestimate tokens, forcing it to act as a strict, reliable upper bound guardrail. In this phase, we bring this prediction into execution. First, our MoPE prediction function gives us our stochastic output estimate. Then we formulate the total cost. It is critical to note that we decouple the deterministic from the stochastic. We take the exact known input count from our local tokenizer and add it to our MoPE output prediction, plus a safety margin. Finally, this total hits our guardrail step function. If the estimated cost is less than or equal to the remaining quota, we execute. If it exceeds the quota, we block the request asynchronously with an HTTP 429 code. Now, what happened as a user prompt behavior changed over time? Static models suffer from prediction drift. To mitigate this without losing our strict upper bound guardrails, we build a continuous asynchronous learning loop. When Gemini successfully processes a request, our middleware logs the actual token usage. When then evaluate this against our prediction using the exact same asymmetrical pinball loss we used for training. By continually applying gradient updates to the MoPE router rate during off-peak hours. We forced the system to perpetually hack the safety line, ensuring our budget rail never degrade. To conclude, we are already looking to scaling this architecture. The second part will show the performance and full report with real data, and we will share the middleware source code to analyze step by step what we implemented. Thank you for your time.